Hi. Today's lecture is about a new kind of reductions called as Turing reductions. And the plan for the lecture is we'll learn about Turing reductions and also the related notion of Oracle Turing machines, which is a beautiful concept by itself. And we'll look at a couple of examples of doing Turing reductions between some of the languages which probably you have seen before. All right. Okay. So the plan is Turing reductions. And this is a new kind of reduction between languages. And this actually generalizes mapping reductions that I'm sure you have seen so far. All right, and it's my personal opinion, but I feel that Turing reductions are more intuitive. So arguably more intuitive. And the added bonus is that while we learn about Turing reductions, we'll also learn about this beautiful notion of Oracle Turing machines, which also generalize the notion of Turing machines that you have seen so far. So we'll learn about Oracle Turing machines. Okay, so let's actually start off today's lecture by learning and defining Oracle Turing machines. All right, so I'll try to formally define them and also build intuition along the way. So let B be any language an Oracle Turing machine M. Okay, so we'll say that Oracle Turing machine M with access to B. So we'll define it in the following way that we'll actually use the notation M with B on the superscript with Oracle access to B is a multi-tape Turing machine with some added features, which is it has a special tape. So it's a multi-tape Turing machine, right? And among its tapes, it has a special tape, which is the, we'll call it the Oracle tape, on which it asks queries of the form. Okay, so it has a special tape, which is the Oracle tape. And on this, it can ask queries of the form, does a string belong to B, right? And the important point is that gets answer in one computation step. All right. Before defining this more formally, so it's sort of like, it's exactly how it sounds like, you have a friend who is an Oracle who knows a lot of things. You can just query him and get an answer to a really difficult question. So in this way, so there's no restriction on B, right? B could be an undecidable language, an unrecognizable language. As long as your Turing machine M has Oracle access to B, it can just cheat and get answers to queries like, does a specific string belong to B in just one computation step. So this is a very powerful generalization of the model of multi-tape Turing machines. And so if we want to define this more formally, so more formally, what happens is, M writes X on the tape, on the Oracle tape, and it asks the question by transitioning to state Q query. So it has a special state Q query on which it transitions and sort of asks the Oracle, like, hey, there's something written on the Oracle tape. Does the string belong to the language or not, right? The appropriate language which is defined by the Oracle. If X is in B, then M goes to the state Q yes, else M goes to Q no. And this is sort of, some formalism if you actually want to write down the transition table of this Turing machine. And, there are these three special states. There's a special tape and so on. So this can be very formally captured as you have seen for normal multi-tape Turing machines. And again, I do want to reiterate the fact that there's no restriction on what kind of language B can be, right? So it's a pretty general model. And as you'd expect, the more powerful B is, the more cool things your Turing machine can do. So here is a really simple observation, which is, B can be decided by an Oracle Turing machine M with Oracle access to B. All right, so this is almost trivial from the definition that, if I give you Oracle access to B, then I can design a Turing machine, which on input M just writes its input on the Oracle tape and gets the answer. So therefore, if B is, say, undecidable or even unrecognizable, MB decides B, right? So with Oracle access, you can, the class of languages which can be decided by Oracle Turing machines is strictly larger than the class of languages which can be decided by Turing machines which do not have Oracle access. Of course, it depends on the Oracle. And if, the Oracle is powerful enough, for example, B is undecidable, then you can actually decide much more, a much richer set of languages. All right, so that's what I want to say about this model. And using this model is kind of the key definition of this lecture, which is Turing reduction. So we'll say that, language A, Turing reduces to language B. So this is written as A Turing reduces to B. So if A can be decided by a Turing machine that has Oracle access to B. All right. So if you can, get membership queries to B in one computation step using this power, if you can come up with a Turing machine for A, then you say that A Turing reduces to B. All right. And this is kind of the key definition that we have for today's lecture. And before thinking about more implications of what it means, what it implies for when A Turing reduces to B, let's actually do a couple of examples and try to get our hands dirty with Turing reductions. Okay, so the first example is kind of simple but really instructive, which is, okay, so define HALTTM to be, MW. The tuple MW says that when run on W accepts the string W. And HALTTM is the complement language. And the claim is that HALTTM bar is Turing reducible to HALTTM. All right. So recall, the proof of this is not that difficult, but it's a really instructive example. Why is that? Well, recall that this language is Turing unrecognizable, whereas this language is recognizable, right? Of course, this is undecidable, but it's recognizable. So, you couldn't have done a mapping reduction from HALTTM bar to HALTTM. It's not possible because that would actually imply that HALTTM bar is recognizable. But Turing reductions actually is a strict generalization. It allows you to do these reductions from unrecognizable languages to recognizable languages. All right. Okay, so let's actually try to prove this. The proof is really easy. What would you do, right? You're trying to design a decider for HALTTM complement given Oracle access to HALTTM. Well, let's just do the obvious, which is, let's say the decider we are doing is THALTTM. So this on input MW uses Oracle access to HALTTM to check if MW belongs to HALTTM, right? And of course, so what it formally means is, given its input, it writes down the input on the Oracle tape and makes a query. And whatever answer it gets, it just flips the answer and outputs it, right? And output flipped answer. And I mean, this is trivially true because if MW is in HALTTM, it cannot be in its complement. And if it's in the complement, it cannot be in HALTTM, right? So clearly THALTTM is a decider for HALTTM complement. And its computation is literally just the time taken to write down its input on the Oracle tape, plus constant time, I guess, to get the Oracle answer and also output its answer. All right, so that was easy, but it also was instructive in the sense that you can Turing reduce unrecognizable languages to recognizable languages. All right, so let's try to do something slightly more complex, which is, so again, familiar languages. So HALTTM, which is, the language of all MW, says that M halts on W. And ETM, which is all M, says that M does not accept any string, right? And suppose, let's try to prove that, so let's try to do a Turing reduction in one direction. So let's try to prove that ETM, Turing reduces to HALTTM. All right. Okay. So what does it mean? It means that suppose you have Oracle access to HALTTM. Can you use this to come up with a decider for ETM? All right, so let's actually try to do this. Suppose, the thing that we are trying to construct, the Turing machine that we are trying to construct is T. So this has access to HALTTM. And it's supposed to be a decider for ETM. So its input is something like M. Okay, and the trick we are going to use for this is something along the lines of other Turing reduction, other reductions that you may have seen before. So what we start off with is actually by coming up with the description of a different Turing machine, which depends, of course, on M. So construct a Turing machine N that on input X does the following. Okay, so we are coming up with a new Turing machine N based on M, which in the following way, that ignores input X. So N ignores its input X. And then what it does is it runs M parallelly on all inputs, and if M accepts a string, then N immediately halts and accepts X. So then N accepts X. All right. Okay. So I guess let's try to maybe qualify what it means for this part, what it means to run M parallelly on all strings. I'm sure by now you're familiar with the notion of enumerating over all finite strings that can be formed by an alphabet. So let S1, S2, dot, dot, Si, and so on be an enumeration of all finite length strings that you can form out of the alphabet. And at ith stage, where you have for I greater than 0, so it's a loop at the ith stage, run M on each of S1, run M on each of S1, S2, dot, dot, till Si for I computation steps. All right. So, I mean, it doesn't really make sense to start from 0, I guess, because the numbers have started from 1. So you take your Turing machine M and run on the first I strings of this enumeration for I computation steps. All right. So this is what it means for running M parallelly on all inputs. All right. Okay. So now what we have done is, okay, so to recap, we are trying to design a new Turing machine T, but we took a detour and came up with a description of a new Turing machine N. And now back to designing T. Okay, so given N, what we do is, so recall that T has access to HALTTM. So what it does is really simple. Uses Oracle to HALTTM to check if n comma 0, belongs to HALTTM. And then it just flips the answer that it gets from the Oracle query and outputs it. So if yes, output no, and else output yes. All right. So that completes the description of T, which is supposed to be a decider for ETM. And note that, so all that happens in the computation of T is given its input M, it writes down the description of the Turing machine N, which functions in the way it's described here, and then uses its Oracle query to check membership in HALT, and this just flips the output, right? Okay, so why does this work? Well, suppose M accepts a string Y, right? Suppose we are in the case where there is some string Y which is accepted by M. So of course this means that M is not in ETM, right? Okay, and it better be the case that T also gives you the same answer. Well, let's see what happens. So if M accepts string Y, then what does N do? N on input X, completely ignores its input, runs M on all inputs parallelly in this fashion. So it, when M is run parallelly on all inputs, it will happen that, M runs for the appropriate number of steps it requires to accept Y. So at some point, at some stage I, some large I, M is going to accept Y. And at that stage, N is going to accept X no matter what X is, right? So in this case, N accepts all strings, right? No matter what its input is, it's just going to accept it. Okay. So what can we say about the query N comma 0? Well, N accepts all strings, so N accepts 0 as well. So it belongs to HALTTM, and hence, we answer, so the query Oracle query is yes, and this is flipped to no, and this is exactly what we want, right? Good. So in this case, T works as we wanted it to work. And now suppose M does not accept any string. Okay, so if M does not accept any string, what does N do on any input? Well, N ignores its input and continues to simulate M on strings, and it never stops, right? So it keeps looping. So in this case, N loops infinitely on all inputs, and therefore N0 is not in halt, which implies Oracle query is no, which implies T outputs yes, right? And in this case, when M does not accept any string, it is indeed the case that, M is in the language ETM, right? Because it does not accept any string. And that's exactly what T outputs. So this actually completes the proof that T is a decider for M, and hence completes the proof that, we have a Turing reduction that we wanted. All right, so this completes the second example, which was, slightly more tricky. And in the next lecture, we are going to see implications of, doing Turing reductions between two languages, and also see that there's, a hierarchy of undecidability. All right, see you in the next lecture.